What I'd like to do now is to discuss with you special cases of the so-called discounted cash flow formula, which we will derive in some other circumstances. The DCF, this is normally the symbols that you use for discounted cash flow formula, is exactly what we're dealing here. The present value is defined as the different cash flows that you're going to have, CF1, CF2, up to CFT, and possibly way more. And you would like to discount them. So to discount, you simply take the interest rate or the discount rate that you're being given, and then you divide these different cash flows by 1 plus r, by 1 plus r squared, up to 1 plus rt. And we're going to discuss several cases now, depending on when you're going to have t being infinity or not. We're going to somehow assume special properties for the cash flows, and the cash flows can be either constant, which is going to be the first case, or they can be growing. When I say growing, they can also decrease somehow. They change over time, but according to a very precise, predetermined pattern. So these are going to be the different cases that we are going to discuss together. So, but the special cases are going to be number one, the case when the cash flow CF1 is equal to CF2 is equal to a constant number, C, and we assume that it's going to be equal to C forever. Forever. This is going to be the time horizon. You can express this by saying that in this case you're going to have t is equal to infinity. So this little symbol here, the double zeros represent here infinity. This is going to be called in terms of formula the perpetuity. The second case that we're going to discuss is going to be exactly similar to this one. We're going to assume that the different cash flows, CF1 is equal to CF2, is going to be equal to C, but that it doesn't hold forever. It's going to suppose to hold only for a finite number of time periods, up to t. And t can be, for instance, 10 years. Semplification, t is going to be equal to 10. So for 10 years you're going to receive, or you're going to have to pay constant amounts per unit of time. Then we're going to have 3. So in terms of name, before I go on with this, we're going to call this here the annuity. The next thing we're going to discuss now is the case where the cash flows keep growing. So we assume that the cash flow in next year is going to be given by C. And then from there on there's going to be a certain growth rate that we're going to denote by little g here. G is going to be the growth rate. And we're going to assume that the cash flow at time period 2 is going to be then C times 1 plus g. And we iterate along this line. So you're going to have CF2 is going to be C times 1 plus g. And in general, the cash flow at time t, it's going to be C times 1 plus g. But now we need to look a little bit at the indices. So for 2 here, you multiply here by a term which is going to be risen to the power 1. And so in general, when you have time t, the power that you have to take here is t minus 1. And so we're going to distinguish 2 cases now, which are going to be first number 3. The case where you're going to have an infinite stream here of growing cash flows. This is going to give you something that's called the Gordon-Shapiro formula. Gordon-Shapiro. And it corresponds to the case where again t is going to be infinity. Case number 4, an analogy with what we had before. It is going to be growing cash flows. So now we write simply growing cash flows. Growing cash flows, and I assume again that for the general term I'm going to have CFT is going to be C times 1 plus g to the power t minus 1, which is also well defined for the first time period. If little t is equal to 1, you get a term 1 plus g to the power 0, which we know is going to be equal to 1. And we are going to have now a finite stream. T is going to be finite. We write this in general by saying t is smaller than infinity. In that case, you're going to deal with a formula which is called the growing annuity. The annuity is growing. So growing annuity. So what I'm going to do with you now is to take you through the simplifying formula, the special cases that you're going to get for these cases, essentially for the perpetuity, a constant stream forever. I'm going to take here the case where you're going to have a finite stream of constant cash flows, for instance 10 years. And then I consider two cases that are going to be related to growing cash flows. In one case it's going to be an infinite stream. In that case you get something that you could call perpetuity, which is growing, a growing perpetuity, or you give it directly the name of the people who use this very intensively in an important way, this formula, which are Gordon and Shapiro. Or you then consider the case as a last situation where you're going to have growing cash flows up to a finite time horizon. In that case you get the growing annuity. We are now in the discussion of the discounted cash flow formula when we are going to have an infinite stream of constant cash flows. This is called a perpetuity. Perpetuity. So we're going to have here cash flows, CF1 is going to be equal to C, second cash flow is going to be equal to C, and so forth. The way that I would like to construct these formulas as a first approach is going to be by using financial arguments, which means shortcuts that correspond to real-life situations, imaginary real-life situations that are going to generate constant cash flows over time. And then I'm going to ask myself, what was the amount of money that I needed to put away to get these cash flows? So how are we going to proceed? The idea is, you give me a certain amount of money, money M, it's going to be a certain amount. Let's imagine that this is going to be 100. I'm going to place these 100 now in a bank account at the beginning of the year. So you're going to have a year here. So this is going to be period t, between time t minus 1 and time t. Here we got t. At the beginning of the period here, time t minus 1, can be 0, 1, whatever. You're going to have here a certain amount, which I'm going to call m. Now the year goes by. How much are you going to have at the end of the year if you get a remuneration of R? Remuneration is R. That's the amount of interest that you're going to get per unit of time. So at the end of the year you're going to get M, which was the initial amount, plus R times M, which is going to be the interest. Now the idea is that you're going to put this interest into your pocket. Put into pocket. Let's take numbers. Suppose that the remuneration here, R, is going to be equal to 3%. You have initially M is equal to 100. How much are you going to get at the end of the year? Answer is going to be M, 100. And then you get the interest, 3% of M. You write this by multiplying the interest expressed in decimal form, not as a percentage. This year is a number expressed in a percentage as a percent. Here you're going to express the percent as in the decimal way, the interest in a decimal way. The M is still 100, and so the total amount that you're going to get in your pocket is going to be 3. How much are you remaining with? Answer, you only have M. But this is exactly the same thing that you started with. So at this stage we have like a perpetual mobile. It's going on every year. You have at the beginning of the year M. Time goes by. At the end of the year you get M plus the interest, which you can remove and put into your pocket. In the case when you had here 100, you could put an amount of 3 into your pocket. You can write this symbolically by saying that you're going to get a certain amount of cash at the end of the year, which is going to be R times M. In the case when we had 100 and 3%, we got here an amount of 3. Suppose now that interest rate remains the same. Suppose that you would like to have a cash flow here of 6. Question, how much do you need to put into your bank account? Okay, so we would like to have 6 is going to be equal to 0.03, and then the unknown here is M. So we see that we can now express one terms in terms of all the others. We can say, for instance, that M This is the amount of money that you need to put into your account to generate then C given R is going to be C divided by R. We can also say, for instance, what we said just right now, if you have M and R, you get a certain amount of cash flows. And if you know now C and M, you can say that the implicit interest that you're going to get in this vehicle, in this investment, is going to be C divided by M. In the case of stock, when you get dividends divided by the price, it's going to be the dividend price ratio, and it's going to be somehow a signal for the remuneration that you're going to get for a stock. The higher the initial value for a given coupon, in that case, the return that you realize is going to be lower. So there's always going to exist an inverse relation between the value or the price of something related then to the returns. The return is going to be higher the smaller the M. If you pay something very little for given cash flows, in this case, you get lots out of it. Big kick. So we have now these three formulas. And the formula that is relevant in terms of the perpetuity is the first one. And instead of saying that we're going to have a bank account in which we place a certain amount of money, we are going to call this here V, and we're going to write that V is going to be then the discounted value of constant cash flows, or C divided by 1 plus R plus C divided by 1 plus R squared, and so forth. And this is going to be equal to C divided by R, the formula of the perpetuity. What I would like to discuss with you now is the annuity. I remind you that the formula for the annuity corresponds to the discounted value of a finite stream of cash flows. So here I have written explicitly in a little diagram what are the cash flows, and I have also placed here the numbers 1, 2, 3 up to big T, which is going to be the last period. What I very strongly recommend to you is always make a little diagram that is going to express from when to when you're going to have the cash flows and how many are you going to have. For instance, if I say to you, you're going to be 30 years old and you're going to receive from the next year on a cash flow of whatever amount, and this cash flow is going to be paid to you till you're going to be 45. In that case, I would strongly encourage you then to write exactly, instead of 1, 2, 3 to T, what are going to be then the ages at which you're going to get the cash flows. Then put numbers 1, 2, 3 till whatever is going to be then the last cash flows, and then you apply the formula. Somehow with the indices, you never know if it's going to be then T numbers or T plus 1, so be extremely careful with this. I remind here what is going to be the formula of the present value of these cash flows. And now I would like to discover with you what is going to be the value of this thing here. As a financier, I reason in terms of portfolios and things that I know already. What do I know already? I know the formula of the perpetuity. The perpetuity is an infinite stream of cash flows. Here I have a finite stream of cash flows that stops at big T. So a financier is going to say, okay, the annuity here is essentially an infinite stream of cash flows of which I have deducted, of which I have subtracted another cash flow, which is also going to be infinite, but which is going to then have as a first cash flow one that would start at time T plus 1. And so we are going to then find what are going to be the values of these two different streams of cash flow. Given by the perpetuity formula, we take then the difference after doing the right discounting, and eureka, we get the present value. So let's do this. We're going to make a little diagram again in terms of timing. 0, time 1, time 2, time 3, time big T. And here now I'm going to write also T plus 1 and so forth. So this is always time. Time, time. I don't write it explicitly because somehow it is so obvious. But the obvious sometimes is not so obvious after all. So let me write it. So here I have cash flow C, which goes to infinity. So if I subtract now minus cash flows that are going to start here, and so I'm going to be having a new referential if you want. This new referential, I'm going to write it in some other column. Okay, so here I have a new referential, and I'm going to have, of course, again time, which is going to have here time 0, time 1 here, and which goes to infinity. Okay. So viewed here from time 0, which corresponds to big T, I'm going to have now a cash flow which is going to be paying here at C, and then again at time 2, which is going to correspond to C. So if I have this cash flow here minus nothing, so it remains C, this cash flow here, which is C, minus this cash flow C, is going to be equal to 0. The cash flows that come afterwards, they're all going to be annihilated. From time 0, you can somehow construct a contract. So the first one is like buying now a perpetuity. The cost of the perpetuity is going to be at time 0, cost of perpetuity, at t is equal to 0. This is going to cost me C divided by R, thanks to the formula that we developed earlier. Now at time 0, I can look forward, and the thing is, here what I bought a perpetuity, which cost me this amount here. I can also sell now something. I'm going to sell something that is going to start essentially at time 0 in the new referential, which corresponds to time t, maybe in 10 years from now. But the first cash flow is actually going to be paid at year 11, the year after. And so on one side I bought something, which is going to give me C. On the other hand, I sold something, which is an event where I will have to pay C. So I take the money from one source and I give it then to the person to whom I promised to give C. So C minus C from time t plus 1 on is going to cancel forever. At time 0 here, the new referential, what is going to be the value here of the perpetuity? Of course, it's going to be again C divided by R. Value of perpetuity sold at t, at big T. This is going to be then C divided by R. But the thing is, we are not interested today. What is going to be the value of the perpetuity at time big T here? We would like to have the value of the perpetuity today. So there's one more thing that we need to do, and this is to bring this value to time 0. And we do this by discounting C divided by R by the right number of units of time here. So this is going to be 1 plus R to the power t, because this new perpetuity, it was somehow sold in the new referential here at time 0 with cash flows that were paid at the time period 1 after. And 0 corresponds to t. Somehow it's trivial, but I insist on this. In that case, now we get the formula for the annuity. Formula, which is going to be giving you the present value here of a constant cash flow stream up to time period t, which is going to be C divided by R, 1 minus 1 plus R to the power t. So how do I remember this formula? The thing is, I have a very bad memory. So for me, I remember that somehow it's going to be a perpetuity, C divided by R. This is sufficiently easy for me to remember, C divided by R. And I have a first perpetuity starts at 0, and then another one that starts at time t. And so I need to subtract the second one. And this is the way that I actually remember the formula here of the annuity formula. The next thing that we would like to discuss is going to be the growing perpetuity that is also called Gordon-Shapiro. We're going to give us a timeline, and here I prepared already the notations. We're going to give us a timeline with today here being time 0, and then we're going to have time 1, 2, 3, 4, for instance, years. Next year you're going to get a cash flow of C, which is going to be growing at a rate here, G here. So we're going to have C, then C times 1 plus G, C times 1 plus G squared, etc. We notice that in terms of indices, the second term here is like C, which multiplies 1 plus G, 2 minus 1. So we have like the time minus 1. We verify that the general formula is going to have then like the time period minus 1. We see it here for time 2. 2 is equal to 3 minus 1, and we see here that this is a term like 1 plus g to the power 0, and to the power 0 is 1 minus 1. So we have here a formula where the time indices here is going to be always guiding us to the power that we are going to have here. The present value then is going to be C divided by 1 plus R, the first cash flow discounted, the second one, and the third one, and notice that there's going to be like a shift in terms of the time here between the growth rate that we're going to take to a certain power, and then the discount rate, which we're also going to raise at a certain power. So don't get confused with these things when you have to do actual computations. When we computed the perpetuity, the idea was to somehow construct a machine where we're going to put the amount of money, the value here of this stream of cash in a bank account, and then we are going to let time go by, and then we somehow have the initial amount, and we are going to then withdraw a certain amount of the cash flows into our pocket, and then we go back and iterate like this. Somehow we would like to do the same, but here it's a little bit more complicated because things are growing. And so the trick that is going to work for us here is somehow going to be using a little bit the same intuition, but using now expressions. We are going to say actually that we have now this present value, which is going to be then this infinite stream, but this infinite stream here contains somehow all the same expressions that we had before, from this point on, if we factor out actually a certain term. So if I had this 1 plus g taken out, I'm going to be exactly like the first stage. And if out of the square here, I'm taking out now 1 plus r, also I would be then at the same stage as I am initially. Formally, we can write that PV is going to be c divided by 1 plus r plus 1 plus g times 1 plus r. And then here we're going to have a term which is going to be exactly the same as we started with up here, which is going to be c divided by 1 plus r plus c times 1 plus g times 1 plus r squared, and so forth, till infinity. And so this term here corresponds clearly to this one here. 1 plus r times 1 plus r is this term squared. This here is squared plus 1 gives you 3, and so forth. So all this makes sense. But what do we recognize here? Well, this is exactly the same thing as we started with. This is going to be PV, the present value of infinite stream here of growing cash flows. Now this is cool because we can write that PV is going to be something like a constant and then a growth rate times the PV. We simplify and we're going to get the expression here of the present value. So now it's algebra. Let me write it stepwise. I'm going to have a PV is going to be c divided by 1 plus r plus 1 plus g divided by 1 plus r, which multiplies the present value. I'm going to multiply both sides by 1 plus r, which is going to take rid of the denominator here. So on the left hand side I'm going to have like 1 plus r PV, and I'm going to have then 1 plus g PV, so I'm going to take this term here and regroup it on the left hand side. It's like writing PV times a certain term, which is going to be 1 plus r, minus the term that I have on the right hand side, minus 1 minus g, is going to be then the term that remains on the right hand side, which is c. Clearly these terms here simplify, and I'm getting now that PV is going to be equal to c divided by r minus g. Now we have an interesting case here. The interesting case is due to the fact that this formula does not really give sense in many circumstances. If we're going to have g, the growth rate, which would be bigger than the interest rate, the discount rate, in that case we would get a value of an investment which is growing very well, which is going to be negative. This is crazy. So it means that somehow we need to impose certain hypotheses. And one of the hypotheses that we're going to make is that g is going to be always strictly smaller than r. If you have r strictly equal to g, in this case we have to go back to this formula, and we would have now c divided by 1 plus r, and then we would have here c divided by 1 plus g divided by 1 plus r squared. But g being equal to r, this is going to be c divided by 1 plus r. And then this term here would also give me c divided by 1 plus r, and we would get an infinite amount of time, c divided by 1 plus r. An infinite amount of c times 1 plus r. Suppose that c divided by 1 plus r takes the value 5. So we're going to have an infinite amount of the value 5. The formula simply explodes, it's going to go to infinity. And so we need to have this strict inequality. When do we use this formula? This formula is going to be applied to circumstances, to opportunities when we're going to have firms that have reached somehow the steady state growth. We're not talking about startups, we have firms that are growing in a regular way, which have been established maybe 20 or 10 years ago and now are in the regular growth rate forever. In that case, it is reasonable to assume that the growth rate of such an investment is going to be then smaller than the discount rate. If you look at me, in terms of height, it's about 181. I'm not infinitely high, not 5 meters or 10 meters. So all the things that are growing at some point grow smaller and smaller. To tell you the truth, there's a moment when you get actually smaller. But this is another issue. But the thing is, we are not going to have things that become too large. Okay, trees have a certain height. Flowers don't become too big neither. Animals don't grow, actually we are all animals, don't grow beyond above a certain size, and this is also what you have here in terms of companies. They don't become too big, at least till now. And so it's quite reasonable to make this assumption here that G is going to be smaller than R. If you don't like this explanation, there would be an economic explanation. And suppose now that you have an opportunity where the growth rate is really very fast, much faster than somehow the interest rate that would apply to this. In that case, what would you expect? We have here an opportunity with a very high growth rate. Everybody would like then to purchase this investment here, which would mean that the price here of this investment is going to be driven up, and it's going to become so high, this price here, that in that case nobody can afford it anymore. In that case, it means that if you're going to have then a price which is going to be very high, it means that we have a situation, nobody wants this investment anymore. And in that case, economically, the growth rate would somehow collapse because nobody wants to buy this firm anymore. The next situation that I'd like to discuss now with you is the growing annuity, which is going to be the last case that we're going to treat here in terms of simple algebra. Again, draw a picture with all the cash flows. We have time 1, 2, and t. We have then the corresponding cash flow, c times 1 plus g, c times 1 plus g to the power t minus 1. Remember, the power that we have here is always time minus 1. And the present value then is going to be given by c divided by 1 plus r. And the different cash flows that we have here, always divided then by 1 plus r to a certain power. And the power here corresponds always directly to the timing. To compute now this cash flow, somehow we are going to use the same trick as we did for the perpetuity. We recognize here somehow that this stream here, which is going to be finite, is going to be like the perpetuity, which is growing, and then from a certain moment on, we are going to subtract a new perpetuity, but where the first cash flow is already then going to be relatively large. It's not going to be C, it is going to be a big cash flow. And so, in terms of intuition, so we want to subtract from a perpetuity, from a growing perpetuity, a new perpetuity of what kind? Well, this new perpetuity starts, it's going to be starting here time t, time big T. Exactly like you have always a time lapse, so you have here the perpetuity which starts at time 0 but pays you the first cash flow at big C, time 1 which is big C, and here we have big T at the last time period, and we're going to have in terms of payments then the first cash flow which is going to be paid here at time t plus 1. So I'm going to write the black referential which is going to be having here t, then t plus 1, t plus 2, this is always time. And in my new referential here, I'm going to have like time 0, time t, time 1, time 2. And the thing is, I'm going to remove now a cash flow that I would have here in an infinite perpetuity at time t plus 1. What is going to be then this cash flow? This cash flow clearly is going to be c times 1 plus g to the power big T. This is going to be then the new perpetuity, the continuation of the perpetuity here, if I had one. So at time t plus 1, I would get c times 1 plus g to the power t. So this is exactly what I want to remove. So I need now to, in terms of value, I'm going to have here the present value of this finite stream. So present value of finite stream, PV, is present value of finite, which means that big T is going to be smaller than infinity, present value of finite stream. This is going to be the difference between the growing perpetuity, so c divided by r minus g, and then I'm going to have here a new perpetuity, minus, that I'm going to subtract here from time t on, and this new perpetuity, it's going to have here as a first term 1 plus g to the power t. This is going to be the first cash flow after multiplication by c, and then I need to divide all this here by 1 plus r to the power t. This is going to be today's value. And the thing is, I'm going to have here this perpetuity, which is going to have as a first cash flow 1 plus g to the power t. And then I'm going to have all the other cash flows that are following. And this means that at time 0, this new perpetuity in terms of value is going to be here at this time period here, c divided, c, which multiplies 1 plus g to the power t, divided by r minus v. And this means that if I bring now this value here from blue referential 0, which corresponds to time t, to today's referential, which is going to be here times 0, in that case I need to divide then the c by r minus g also. I repeat, I'm going to have a first perpetuity which is growing till infinity, so the terms here would continue in my thought experiment now. It goes to infinity, but given that I have only a finite stream up to time t, I need to subtract all the cash flows that start at time t plus 1. If I have a cash flow that starts at time t plus 1, well, the cash flows, if this perpetuity would continue, would be c times 1 plus gt. So the first payment that I need to have for my new perpetuity starting at time 0 is going to be then c times 1 plus g in terms of t. The value here at time 0, blue referential, of this infinitely growing perpetuity would be c times 1 plus g to the power t, first cash flow, divided by r minus g here, r minus g here. And somehow I'm not interested in this value here at time 0, blue referential, which corresponds to 10 years from now. I'm interested in the value today. And so I need to discount this to today, down to today. Now I'm done. I can write now the formula for the growing annuity, and I get that the present value of this thing here is going to be equal c divided by r minus g, which multiplies 1 minus 1 plus g divided by 1 plus r to the power t. So this here is the formula of the growing annuity, and to remember this, I remember that it's again like in the case without growth rate, it's going to be a perpetuity, this is the value of the perpetuity, growing here, minus a discount factor, and I need to remember that discount factor somehow needs to take into account the growth rate, which is going to be captured here by this term here, 1 plus g. So after all, it's relatively easy actually to remember this formula. This formula is very important in the context of pensions. You can think about the case when you save during your lifetime, your lifespan, and you're going to ask yourself today, what is going to be like the discounted value of the future savings that I'm going to make over time? And the savings are going to be related then to your wage, which grows over time. And this formula then tells you what is going to be this value. And then you can project it to when you're going to be going into retirement. This is going to be like your savings retirement, and from then on, given that you have no income, you're going to dissave actually. In practice, when you take a credit, very often it's going to be as an annuity. You're going to get today a certain amount of money, and then you make regular installments, payments to the person who gave you the money. But the thing is that you're not going to make annual payments, you're going to pay a certain amount per month. It could be also weekly, daily, quarterly, but in most of the cases it's going to be actually monthly. And so you would like now to adopt the annuity formula to the case where you're going to have then monthly payments. I'm going to denote in general M, the number of sub-periods that you're going to have in a year. So if you have 1 year here, 1 year, I'm going to assume that you're going to have like M sub-intervals. Think about M as being month. In that case, you're going to have 12. The banker when he or she actually gives you the credit, is going to quote an annual interest rate. This is a definition, it's a given. I'm going to call now A sub m the annuity per sub-period, call this the monthly annuity that you have to pay. In that case, the present value of the monthly payments is going to be given by the following formula. It is then the regular formula for the annuity, A sub m, and then you take, this is now a definition. You don't have to ask why it is like this, it is a convention. It's a definition or a convention, and by definition, a convention is something that is like given. It's like when I say hello to you in the morning, it is just like this, you have to do it. And so you take r divided by m, and then here you're going to have then the perpetuities that you're going to subtract from the first one. So this is going to be the term 1 minus 1 divided by 1 plus r divided by m. But now you need to be a tiny bit careful. The thing is that normally we had here t here. T, this is going to be the number of units of time. So we're going to use t expressed in terms of years. So t expressed in terms of years, expressed in terms of years. And we're going to multiply this by m, which is going to be then the frequency by which you're going to make payments during a year. So if you have 1 year credit, in that case you're going to make 12 payments. And you're going to have t is equal to 1, and you're going to make m 12 payments. If you have now 3 years and a half, 3.5 years, it's easy to verify that the number of t times m is going to be 42. I'll let you do this. You can do it in your head. So this tells you now what is going to be the discounted value if you're going to make then monthly payments for a given annuity, and the banker is going to quote you here a certain interest rate, which is going to be r. Very often somehow you need to go the other way. You're going to be given a certain amount of money, and then the question is going to be, what's the monthly annuity that I need to pay? And so you need to invert this formula. At the direction, given a credit of k, what is my monthly annuity? This is the question, and the answer to this is that the monthly annuity is going to be A sub m, is going to be then the credit. The credit here takes the place of the left-hand side, the value that you were given at the beginning, which multiplies r divided by m. And then you need to divide by the term here that you have in parentheses. So I simply rewrite it like 1 divided by 1 plus r divided by m to the power t times m. And these formulas are typically then implemented in an Excel spreadsheet so that you can use and play with them. So you take the initial credit, you multiply by r divided by m, and then divide it by the difference of perpetuities, and this gives you then the monthly annuity. Very important formula if you want to get the credit.